My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome to all you in our International Physics webinar. And today it's our 66th International Physics webinar. So good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. Hope you are well and safe from Corona pandemic. So all we know that we are staying in a Corona pandemic situation. And we know that the most devastating epidemic of 21st century is the coronavirus or COVID-19. So all the institutions have been shut down due to corona pandemic since March 2020. So we cannot continue our normal academic program inside the campus. So to continue our program, we have to start online program. So our Department of Physics, Pabna University of Science and Technology has already started its online program, including online classes and online international physics webinar. And I'm happy to share with you all that we have completed successfully our 65th international physics webinar, and today it's our 66th. And we are trying to adjust with this new normal situation. And today is a very important day for our department. Today, I would like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Center of the Interdisciplinary Exploration and Research in Astrophysics, CIERA, Northwestern University, USA, in Astrophysics. And we have with us here today Dr. Sukrit Ranjan, Postdoctoral Fellow at the CIERA, Northwestern University, and research affiliated Blue Marble Space Institute of Science, USA. And he has already connected with us, so I'd like to welcome our speaker. So good evening and a very good morning to your part. And welcome to our International Physics webinar. Welcome to Bangladesh and our university.
Thank you very much. It's an honor to be here today. Very grateful.
Yeah, we're also grateful to you for accepting our invitation. So the main aim of our program is to motivate and encourage our students in this corona pandemic situation. So for those who are new, I'd like to inform that we are divided our webinar into three parts. First of all, we'd like to introduce our speaker with all of you, and then there is a time our speaker will deliver his speech, and at the end we have a discussion session. In that time, anybody can join with us. So I think you have already come to know the title of our today's International Physics webinar. Title is the Phosphine on Venus. So, and our speaker is Dr. Sukrit Ranjan. He's currently working as a postdoctoral fellow at Center of Interdisciplinary Exploration and Research in Astrophysics, CIERA, Northwestern University, and a research affiliate Blue Marble Space Institute of Science, Washington, USA. And he's a CIERA postdoctoral fellow at Northwestern University and an affiliate research scientist at BMSIS. He is also a planetary photochemist interested in using the interaction of molecular system with energetic radiation as a lens to study life as a planetary phenomenon. His research focuses on applying photochemistry to questions related to the origin of the life on Earth and the search for life on other worlds. So these questions are coupled. Efforts to understand the origin of life on Earth helps guide our search for its elsewhere in the cosmos, while observation of the other planets help us to test our theories of the prebiotic environment and the abiogenesis. So to understand abiogenesis, he works to constraining the palette of environmental conditions from which life arose on Earth, to constrain the guide experimental studies of the origin of life. To search for the life elsewhere, he works to determine observational tests by which life on other worlds may be remotely discriminated. In collaboration with his experimental colleagues, he works to obtain the critical measurements of fundamental photochemical parameters required to build robust model to support of both goals. If we see his educational background, you can see he has completed his PhD degree from Harvard University in astronomy and astrophysics in May 2017. And his PhD thesis title is The UV Environment for Prebiotic Chemistry. And also he's a MIT SB Physics June 2010, a major in physics, minors in history and astronomy. So we can see his professional appointment. He's currently working as a postdoctoral fellow at Northwestern University, CIERA, from 09 2020 to present. And at MIT, it's called postdoctoral fellow from 09 2017 to 08 2020. So professional career, other appointments. So at Blue Marble Space Institute of Science, he also worked as a research assistant. He's still now working there, and also worked as a short-term postdoctoral researcher at Indian Institute of Astrophysics, and also at NASA Arms Research Center. So we can see his awards and honors. He got postdoctoral fellowship from CIERA in 2020 and NAI Early Career Scholarship in 2018 and AS Roger Doxy Prize in 2017 and Simon Collaboration on the Origin of the Life Postdoctoral Fellowship 2016 and Harvard Astronomy Department Outstanding Mentor Certificate in 2014 and 2015 and AGU Fall Meeting Outstanding Student Paper Award in 2013 and Harvard University Certificate of Distinction in Teaching in 2012 and NSF Graduate Research Fellowship in 2010 and Joel Matthew Orloff Award for Outstanding Service in Physics in 2010 and NASA Ambassador for International Year of Astronomy in 2009. So you can see his teaching and mentorship and his recent publications. So thanks all for all of your patience. Now it's time to go to our speaker. So thanks again for accepting our invitation. So it's your time, you can start your session.
Thank you very much for that wonderful introduction, Pretam. Hi, everyone. My name is Sukrit Ranjan. I'm a CIERA Postdoctoral Fellow at Northwestern University. And I'm excited today to be presenting this international physics webinar focused on the our recent discovery or our recent reports of phosphine on Venus. I understand that this is meant to be heard by a broad audience primarily targeted at students, so I hope you'll forgive me for including some pedagogical material as well on big picture motivation. So without further ado, I'll jump into the talk, and I've tried to leave plenty of time for questions and follow-up, so please feel free to ask questions vigorously as you see fit. Okay, so in terms of the big picture motivation for the work I'm going to share with you today, are you able to see my screen, by the way? Is that good?
Can see.
Okay, wonderful, yeah. So there's a few questions that have been with us as human beings, as a human species, for almost as long as we've been around. Some of those questions we've been able to answer in the last few centuries. For example, the question of, can we fly? Well, now we know we can do that thanks to the invention of airplanes. How old is the universe? How did it start? That's also a question that we have been asking for many millennia, but we finally have firm constraints on the answer to that question as well, thanks to missions like Planck and the discovery of things like the Big Bang Theory. One question which still eludes us, which we have wondered for many, many millennia and continue to wonder today, is the question of, are we alone in the universe? That is to say, is life on Earth unique, or is there life elsewhere out there on other planetary bodies or in other stellar systems? This is a question which we have wondered for a while. We've tried experimentally to solve it for some time now with missions to other planets, but it remains elusive, and we still don't have a good answer to that question. So this is the kind of question that that the work I will share with you today is focused on, trying to understand whether or not we are alone in the cosmos. And from an astronomical perspective, this is a...
Excuse me, I think we have a problem in the slide. We cannot see full screen.
Let me try that again. Are you able to see it now?
Yeah, now it's okay.
Okay. Is it still good?
It's okay.
Great. From an astronomical perspective, this is an exciting time to be thinking about this question, because governments and space agencies and space companies around the world have, for the last several decades, invested considerable scientific resources in trying to answer this question. Within our own solar system, efforts have focused on identifying potentially habitable niches, environments where life as we know it could perhaps emerge and endure in planetary environments. And this effort has been very successful. We've identified many potential habitable environments in our own solar system, including the subsurface brines on Mars, where you have very salty, very cold, but nonetheless liquid water in the interior of Mars, in the subsurface, where it's relatively warm and it's able to survive. We've identified the clouds of Venus as a potentially habitable environment where surface liquid water coexists with habitable temperatures and pressures. The icy moons of the gas giants of the outer solar systems, like Europa and Enceladus, we now know host massive subsurface oceans, which might have hydrothermal activity capable of sustaining life as we know it. Perhaps most exotic is Titan, whose surface hosts lakes of liquid hydrocarbons, ethanes and things like that, which raises the question, could life arise in non-polar solvents other than water? Because if it could, Titan has a lot of them. So, and efforts over the past few decades have identified these environments, and even more efforts are now planned to probe them and see not only could life as we know it exist there, but does life as we know it exist there? The search for so-called biosignatures, markers of life as we know it. And the last decade or so, the search has broadened beyond our own solar system. In 1995, the first planets orbiting other stars were found, and in the decades since then, we've radically expanded the number of worlds we know about. This is a plot showing the population of observed worlds, of observed exoplanets, planets orbiting other stars. It's a few months old, which probably means that it's already quite out of date. The pace of planet discovery is quite fast, but it's nonetheless illustrative. So let me walk you through it a little bit. On this plot, each individual point is a different planet that's been discovered. On the x-axis is semi-major axis, or how far the planet is from its host star. On the y-axis is planet radius, or how large the planet is. The colors represent different detection techniques, the most important of which is the one in yellow, called the transit method, which I'll get to in the next few slides a little bit. This is by far the most prolific method for planet discovery. And it's the method that's generated by far the most planets through missions such as the TESS mission and through the Kepler mission. Now, you'll notice that some of these points have white circles around them. Those are the planets for which we have some constraints on the existence of an atmosphere. And this is another point that I'll get to in a moment. But right now, just the big picture is that these white circle points are the planets for which we have atmospheric measurements. For the more massive of these planets, large, massive planets orbiting close to their stars, planets in this regime over here, we've been able to go a little bit further. And for some of them, we've actually been able to measure spectra of the planet's atmospheres. For example, this spectrum shown here from Wakeford et al. 2018 for a hot Saturn exoplanet. That's a planet roughly the size of Saturn, but orbiting much closer in. Warm Saturn exoplanet. It's a planet the size of Saturn, but orbiting closer to its host star relative to Saturn in our own solar system, such that its temperatures are much higher. And for this object, Wakeford et al. Were able to detect not only atomic species like sodium and potassium in the atmosphere of this planet. So not only have they shown that these planets contain sodium and potassium, they've also been able to detect molecular species, in particular water vapor, which is very exciting. You might ask how they go about doing this. To answer this question, I'll have to take a few moments to walk through some of these detection techniques. In particular, I'd like to touch on the transit method. The transit method for planet search and for planet characterization sounds so ludicrously simple that you might well think that I'm hiding something, but I'm really not. It really is that simple. And what the transit method relies on is the observation that some planets will appear to pass in front of their star. So if we're looking at a star, some planets, as they go around their orbits around their host stars, will appear to pass in front of it from our point of view. When they do that, the star will appear to dim slightly because some of the light being emitted by that planet being emitted by that star will be blocked by the planet. That's shown here in this plot over here. So when the planet is not blocking the star, you have a high amount of sunlight. At this point 2 over here, the planet just starts to block some of the light of the star, so the brightness decreases. And then as the planet is transiting the star, when it's kind of in the middle, the maximum amount of light is blocked, and the brightness has gone down the most. So these effects are small, very small, typically percents or minute fractions of a percent often. But we can still look for them. Modern equipment is good enough that we can look for these subtle drops in brightness. And by doing so, we can detect these planets orbiting other stars. And this is by far the most prolific method for planet search. In addition, for planet search, such planets, these so-called transiting planets, also offer an almost unique opportunity for atmospheric characterization. And the reason for that is that for some of these planets, for these transiting planets, that starlight is going to filter through the terminator region of the planet's atmosphere. It's going to filter through the annulus of the planet's atmosphere. And that's what the gases in that atmosphere are going to absorb selectively absorb some wavelengths of that light. They're going to imprint a transmission feature on its spectrum. If we pass that light through, concentrate that light in a telescope and then pass it to a spectrograph, we can measure absorption spectra. And we can figure out what the composition of that planet's atmosphere is. So it's, again, a very simple, deceptively simple technique in theory. In practice, it's very hard in the sense that these are very subtle measurements. There's a lot of systematic effects, and you have to be very careful about removing those systematics. But it's nonetheless something that can be done, is being done now, and will be done in even more depth in the future. So the bottom line takeaway message is, for this class of planet, we're actually able to directly detect atomic and molecular components of its atmosphere, even from many light years away, which is really exciting. And so this raises a kind of exciting question. Today, with the instruments and facilities we have today, we can characterize the atmospheres of giant planets or other stars and search them for evidence of molecules like water. In the future, with the next generation of instruments, for example, the extremely large telescopes being built on the ground, or the James Webb Space Telescope due to launch any day now, or even the next generation of space observatories like HABEX or LUFOR, we hope to characterize the atmospheres of smaller, rocky, potentially habitable exoplanets, of which a large number have been found. So these are planets that are roughly the size of the Earth. We think they're rocky, just like Earth is, and they orbit at a range of distances from their host star that is compatible with the existence of surface liquid water. So we're not saying there's surface liquid water there, but if liquid water were there and the planet were similar to what Earth is, it would be stable there. So these are good places to take a look at in terms of habitability and in terms of searching for life beyond Earth. And in the upcoming decades, we will have the ability to do just that, kind of closing the loop on why this is such an exciting time astronomically. So how are we going to go about searching these planets for evidence of life? The dominant paradigm for doing so is the so-called Biosignature Gas paradigm. The idea behind it is this. Again, today we can characterize the atmospheres of giant exoplanets and look for molecular molecules in their atmosphere. Perhaps in the future we can do that with rocky exoplanets. If we did that for Earth, so I want you to pretend for a moment that you're not on Earth, you're on a planet you're on one of these exoplanets, and you're looking back and you've just successfully measured the spectrum of Earth as an exoplanet. Earth's from many light years away. If you had a sufficiently good telescope and sufficiently good data cleaning techniques, this is something like what you might see. This is the spectrum of Earth as an exoplanet. And we see here a number of molecular features. We see molecular signposts of molecules like ozone, oxygen, water vapor, carbon dioxide, and so on and so forth. And there's a few exciting things here. One of which is, if we know how rocky planets work, and at least if we look at the rocky planets in our own solar system, there's a few molecules we don't necessarily expect to be there based purely on abiotic processes. For example, oxygen. Oxygen in our own planet's atmosphere is biogenic. To our understanding, in the absence of oxygen, without the presence of plant life, we wouldn't have any oxygen in our atmospheres. So in the absence of life, in the absence of plant life in particular, this O2 feature wouldn't be there. So this raises the question, perhaps we can use molecular signposts like the existence of O2 in our atmosphere as probes of biology, as probes of whether or not biological activity is present on a planet's surface. An ideal biosignature gas would be produced is one that would be produced by life. So it would be produced by life as we know it here on Earth. It would be spectrally distinguishable in the sense that we would be able to differentiate it from other gases here on Earth, or that would be present in the atmosphere. You'd want it to have no abiotic false positive scenarios. In other words, you don't want abiotic production mechanisms like volcanism, lightning, impacts, atmospheric chemistry, and so on and so forth to produce the gas as well. because then how could you differentiate between the biological and abiotic production mechanisms? And the final thing is you need it to be detectable. You need it to be able to accumulate to detectable concentrations on habitable planets. And then remember, that's quite a hard constraint because these planets are very, very far away, many, many light years far away, trillions of kilometers far away. So it's quite challenging to characterize their atmospheres and detect molecular signposts. So this is what we'd like to do. We face a little bit of a challenge because the ideal biosignature gas has not yet been identified. We haven't yet identified a gas which meets all 4 of those criteria. The canonical biosignature gas, the kind of gold standard that we've thought about for some time, and this is a typo over here. This should be as identified by Carl Sagan in 1993. This is the typo. This shouldn't be 2013. Is the combination of methane and oxygen, coterminously with water vapor. And this would in fact be a very robust biosignature because you would, in order to both have a reducing gas and have an oxidizing gas, you need rather high fluxes of both. And it's hard to imagine abiotic processes that could robustly generate both. However, there are certain fundamental observational challenges, the most stringent of which comes from the detectability constraint. If you try to simulate detections of these molecules throughout geological time, and you look at Earth as an exoplanet throughout its history, you find that there's no epoch in the history of Earth so far where both oxygen and methane were simultaneously detectable. So again, this is a little bit of a busy plot. Let me walk you through it. On the x-axis here is time. So on the right edge is the present day. On the left edge is the very earliest epochs on Earth. The y-axis is detectability. This white shaded region corresponds to gases that are detectable. And this gray shaded region corresponds to gases that are not. And these are different molecules. And so today on modern Earth, there's enough oxygen and ozone in our atmosphere that we could detect it on Earth as an exoplanet, but not enough methane. The methane signature just isn't strong enough. In the mid-Proterozoic, a few billion years ago, none of these molecules was really detectable. And in the deep past, methane might well have been detectable, but oxygen and ozone were not detectable. They weren't present at high enough concentrations. So it's not really possible to get both of these gases at the same time, which is what you really want to do. We might well be restricted to single biosignature gases. And if that's the case, we're in a much tougher situation because we haven't identified a single ideal biosignature gas yet. To rectify this problem, our team at MIT has been conducting what we call the All Small Molecules project for some time. And it's essentially an effort to expand the catalog of potential biosignature gases. So what we do is we take all the small volatile molecules that life produces, and we try to evaluate them using different criteria as potential biosignatures. And we try to assess how good or how bad they are. So this is just a plot. So I'll just skip past that for a moment. The first gas that we have evaluated as a biosignature, the very first one that is passed through our full pipeline, is this gas that I'm going to focus on in this session called phosphine, pH3. pH3 is quite a simple molecule. It consists of a phosphorus, that's this kind of orange-red thing over here, connected to 3 hydrogen atoms. Those are these 3 white little guys over here. So it's a very simple molecule, just 4 atoms. It has several advantages as a biosignature we found. In particular, it has strong distinguishable spectral features. It has 3 spectral features. The one at 10 microns in particular should be quite possible to differentiate from other components of planetary atmospheres. It seems to lack false positive mechanisms that we know about. We looked at a whole bunch of different abiotic mechanisms for the generation of phosphine on terrestrial planet environments, and we weren't able to find any. So that we are not aware of any geological mechanism by which phosphine can be generated. So if you detect phosphine, it's almost certainly due to life on a rocky if you detect in significant concentrations on a rocky planet. But phosphine as a biosignature has one major weakness, and that is that it's extremely efficiently photochemically destroyed, by which I mean UV light and UV light-driven processes are very efficient at clearing it out of the atmosphere. We did kind of a simple photochemical calculation, and what we found is that in order for phosphine to build up to detectable concentrations, it has to be a major product of the biosphere. So in order for it to be detectable, you want it to be present at least parts per million concentrations. That's what this plot is showing over here. So on the x-axis is molar concentration of the different gases, molar concentration. And on the y-axis is altitude. Here I'm simulating a planet with an H2-dominated atmosphere orbiting the nearby M-dwarf star GJ1214. And the solid line are phosphine concentrations for different phosphine surface emission fluxes. And the key thing to note here is that in order for phosphine to become detectable, in order for it to reach the near parts per million concentrations that are required for robust detections, you need fluxes of on the order of 10 to the 11 molecules per square centimeter per second. And that's really huge fluxes. That's fluxes that are comparable to the methane generation flux on Earth. And methane is a major, major product of our biosphere. So in order for phosphine to be detectable, it can't be a minor product of biology. It needs to be a major product of biology. And even if it's a major product of biology, it's only detectable in certain planetary environments. In particular, in order for it to be detectable, you need it to be on an exoplanet. You need it to be in a puffy atmosphere, a planet with low mean molecular mass, for example, one dominated by H2, by hydrogen gas. And in addition, you need it to be specifically on a planet orbiting a kind of low mass M-dwarf star. And that's because those planets are low UV environments, which I'll touch on in a moment. So what are M-dwarfs? What is this particular kind of star that I said is the only place you can really look for phosphine as a biosignature on an exoplanet? M-dwarf stars are small stars that are smaller and cooler than our own sun. So this is kind of showing you two stars. One is our own sun, a large yellow star, and the other one, kind of to scale, is this M-dwarf, in this case Kepler 186. And you see that this star is a lot smaller, cooler, and redder than our own sun. And this ends up having a lot of observational advantages. Not only are they low UV, but they're also smaller intrinsically. So the transit spectrum, the atmospheric imprint of the amplitude of the signature of atmospheric absorption, its amplitude is relatively stronger, so it's easier to detect. And in addition, one thing that's sometimes omitted is that they're the most common type of star in the galaxy. So this is a graphic from the Recons project showing showing the abundance of different stars in our solar neighborhood, and we see that these smaller, cooler M-dwarf stars are by far the most common type of star in the galaxy. They're on the order of, like, I think something like 80, 90, 70, 80% of the stars in our solar neighborhood and in the galaxy as a whole. And one of the key things for them, for our point of view, is that they're very low UV environments. So to illustrate that, here's a plot from CIERA et al. 2013. On the x-axis, you have this is just showing you the emission wavelength of different stars. On the x-axis, you have wavelength in nanometers. On the y-axis, you have the flux at the habitable zone equivalent of the Earth-Sun distance. The black line is what our own sun is putting out. And in comparison, these colored lines are the limiting cases on what an M-dwarf star, analogous to GJ1214, might be able to put out as well. And the key thing to take away is that the sun puts out orders of magnitude more UV than M-dwarf stars, and as a consequence, it's orders of magnitude easier to build up build up biosignatures on planets orbiting M-dwarfs compared to planets orbiting sun-like stars. And so that's essentially what we found over here. So for an otherwise identical planetary scenario, if you're on a planet orbiting an M-dwarf, you have about 2 orders of magnitude more phosphine compared to a planet orbiting a sun-like star. So, and this is not a new idea. This was also demonstrated for methane by Segura et al. In 2005. But it's something that is really, really quite important for phosphine, because phosphine is even more vulnerable to photochemical destruction than methane is. It's just really efficiently destroyed by all kinds of UV radiation. So the overall takeaway is that M-dwarf planets are the only kind of exoplanet, the only kind of planet orbiting out of the star that you could realistically hope to look for phosphine. It's kind of a lost cause for sun-like stars. As an aside, this also kind of raises an interesting idea. So M-dwarf planets are really ideal for searching for life as we know it. But it turns out that from the perspective of certain kinds of origins of life chemistry, certain proposals for how life got started here on Earth, they're really bad environments. And that's, again, due to the fact that they have very little UV. So this is work that was led by Paul Rimmer in 2018. And what Paul showed is that there's been a chemical mechanism that's been proposed for some years now to be the synthesis mechanism for RNA, ribonucleotides, one of the key molecules for life and the fundamental requirement for the origin of life in the RNA world hypothesis. And Paul showed that particular mechanism can't operate on planets, on these kind of low mass planets, because it requires UV light, and those planets just don't have enough UV light. And so this raises a kind of exciting idea, which is that so these M dwarf planets should be ideal biosignature test cases. If there's biology there, it should be quite detectable. But according to this theory, this UV requirement theory, you shouldn't find life on planets with such low UV outputs. So this raises a kind of attractive idea that perhaps you can use a life test you can use life search on exoplanets to test theories of the origin of life. In particular, if you find life on these M dwarf planets, that demonstrates that UV is not required for the origin of life, which strongly constrains theories of abiogenesis. There's a major caveat here, which is that M dwarfs are flare stars. They flare frequently, they flare often, and when they flare, they put out much more UV. It's possible that these high levels of UV can substitute for this lack of steady state UV. Experiments are underway to constrain this possibility a little bit more, but this is kind of the way we want to use these planets as ways to test different theories of the origin of life as well. So, kind of the takeaways from the first part of the talk. We talked a little bit about phosphine as a biosignature, and we started looking at it because we're trying to identify kind of what might one of these ideal biosignature gases be, because none of the ones we have right now are quite good enough. We've evaluated phosphine and found that it's a good signature of life if you can see it, but it's tough for it to build up to detectable concentrations on exoplanets. It needs to be a primary product of the biosphere, and you need to be on a very particular planetary environment. You can kind of turn this lemon into lemonade, though, in the sense that the kind of planet you need it to be, that is to say an M dwarf planet, are also one of the most interesting classes of planet from the perspective of theories of the origin of life, in the sense that if you detect life there, perhaps, just perhaps, it might be an opportunity to constrain theories of abiogenesis, to kind of experimentally test the environmental requirements for the origin of life. So that's where our study stood as of kind of a couple of years ago. At that point, we had most of the results in. We'd evaluated phosphine as a biosignature. We'd concluded that, well, if you see it, it's a pretty promising sign of life, but it's unlikely that it'll build up to detectable concentrations. And we kind of put it to bed and focused on other tasks at that point, which just goes to show that nature can always surprise you. Because early last year, we were reached out to by some of our observational colleagues in the United Kingdom, who reached out with a really unexpected finding. They reported that they had detected phosphine at concentrations of about 20 parts per billion in the atmosphere of Venus. And these are these data that are shown over here. I'll go into more depth later. So specifically what they'd done is they'd first started by pointing to the James Clerk Maxwell telescope at Venus. And they'd measured a spectrum shown here in white, which had opacity corresponding to a feature of phosphine. So there was absorption here, which they attributed to the presence of phosphine. That was a relatively low signal to noise detection, though. So they went and re-observed it with another more powerful telescope, in this case, ALMA. And those kind of higher signal to noise data are shown here in orange. And they again detected opacity at that feature, which they attributed to phosphine. And so this is kind of extraordinary because it looks like a reasonably robust detection, in that it was the same opacity was detected using two different facilities at two different locations and epochs, and using two different data reduction techniques. So that seems relatively robust, and that's quite astonishing. Let's look at those data in a little bit more depth. Here I'm showing you a close-in on a figure from our paper. This is a kind of whole planet spectrum this is kind of the whole planet spectrum from ALMA, again showing a sharp opacity at wavelengths precisely corresponding to phosphine. This is showing it by location on the planet, and here what we're seeing is that phosphine is heterogeneously distributed. In other words, it's not present at all parts of the planet. It's specifically only present at the mid-latitudes, shown here in blue. It doesn't seem to be very present in either the polar or equatorial regions. So it's not uniformly distributed throughout the atmosphere, it's only present at certain places. And that's not entirely unexpected, in the sense that, as I'll get to, we expect phosphine's lifetime to be short in the atmosphere, but it is a kind of worth thinking about a little bit more closely. So I want to emphasize here that all I've shown you so far is a detection of opacity, a detection of a molecule which absorbs at that particular wavelength corresponding to phosphine. But These spectrographs are not perfect. They have some finite width, and that always raises the possibility that perhaps there's some other molecular feature there that's absorbing there as well. So maybe it's not phosphine, maybe it's something else that absorbs exactly at that wavelength regime. One of the things we try to do in our work is try to evaluate other kind of potential spoof molecules, other molecules which might be imitating that feature. Now, in some sense, this is always going to be an incomplete work, because we actually don't have complete spectra of many of the molecules we expect to find in the Venusian atmosphere or in rocky planet atmospheres generally. Our data, our sets are just not complete. We have to do a lot more kind of experimental spectroscopic work before we can confidently know all the spectral features of all the different molecules. So all we can do is look in the literature and ask what has been reported so far that might be a confounding molecule. One confounding molecule might be sulfur dioxide, SO2. SO2 we know to be present in the Venusian atmosphere. It's actually quite common there. And SO2 does have a feature that's relatively nearby this phosphine feature. So this raises the question, could sulfur SO2 be spoofing our pH3 feature? To test this possibility, my observational colleagues did something I personally thought was quite clever. What they tried to do is they looked for another known, SO2 is known pretty well. So in their same data set, they looked for another feature of SO2, another kind of wavelength regime where SO2, if it was present, should be absorbing, and tried to ask if they could see any evidence of that. And that's this data set on the left in this plot over here. So the black is their actual data. The kind of bolded black region over here is where SO2 should be absorbing, where you should find a dip if SO2 were present. And the key thing to note here is that they're not able to find a dip. Even when they clean up their data in favorable ways, they're not able to reproduce a dip. This dotted line over here corresponds to how deep an SO2 feature would be present if if it could still be compatible with their experimental constraints. So this is their upper bound of the amount of SO2. You can't have more than that according to their analysis. And so you could ask, well, supposing you had that amount of SO2, how would that look like in your molecular feature over here? And the answer is it would look like this little green curve over here. So it could only explain this little green curve's amount of the opacity. If you subtract out that SO2 contribution from the overall signal, you still end up with this red line over here. So you still have a gigantic signal, which requires significant amounts of phosphine to explain. So this was our argument for excluding SO2 as a source of opacity and ruling in phosphine instead. So that's the key thing to keep in mind moving forward. So it appears that phosphine is in fact present in the atmosphere of Venus, at least according to our data and our analysis, and that's extremely surprising because it shouldn't be there. Photochemistry, UV-driven processes should destroy phosphine in the Venusian atmosphere very, very robustly. Let me explain to you a little bit what I mean by photochemistry. So you can think of this as a map. This is a map to the spectral regions of stellar emission. So over here in the yellow, so the black line is the spectral output, the spectral energy distribution of the nearby M-dwarf star GJ832. In the yellow is the visible and near infrared part of the spectrum. And this part of the spectrum is very important for kind of planetary climate. It sets the planetary temperature pressure profile to large degrees. So it's responsible for climate, for thermochemistry. But it's not otherwise important for actual what I'm going to call photochemistry. The blue region over here is called the XUV radiation. It's the very shortest wavelength radiations, the most energetic particles. These particles are all absorbed very high in the atmosphere of the planet. They're very important for processes like atmospheric escape, but they're not as important for planetary chemistry, and particularly the chemistry of the lower parts of the atmosphere, the stratosphere, the troposphere, and so on and so forth. The part of the stellar spectrum that's important for that is the so-called UV range, from about 100 to 300 nanometers. And this is the part of the spectrum which completely sets the photochemical state of the planet's atmosphere. And the fundamental reason for that is illustrated in this plot over here. Again, the top plot is just a spectral energy distribution. Here I'm showing the SED from the sun compared to an SED from one of these low UV M dwarfs. The y-axis now goes from about 100 to 300 nanometers. So I've tried to zoom in on the chemically important part of the spectrum. And the bottom plot here is showing just the absorption features of different gases. So the key thing to note here is that almost every atmospherically important gas absorbs in this wavelength regime. And that just happens to be because this wavelength regime corresponds to the energies of covalent bonds. So these are the photons of these wavelengths happen to have energies, the right amount of energy to interfere with the kind of electronic states of molecular systems and therefore be absorbed by them and trigger chemical change. And they can trigger a broad variety of important chemical processes, including photolysis, where they break up a molecule and create reactive radicals, which can do subsequent chemistry. They can also do photoionization, and they can do photoexcitation, both of which trigger other chemical processes, but all of which tend to be destructive for biosignature gases. If you include the effects of these processes, you find that pH3 should not really be present in the Venusian atmosphere. It should be photochemically quite efficiently destroyed. To illustrate this plot, to illustrate this, we did a calculation that's shown here on the right. This is the part of the work that I led, so let me walk you through it a little bit. The bottom plot over here is the overall lifetime of phosphine in the atmosphere of Venus. And I've broken down the lifetime into two parts. So you have lifetime in seconds on the x-axis over here. Note that it's a log scale. You have altitude in kilometers on the y-axis. The purple dashed line over here is the photochemical lifetime. And that's the lifetime if you take a molecule of phosphine and you hold it at a fixed altitude in the atmosphere. About how long do you expect it to last before being destroyed by chemical processes? And the chemical processes we considered were attacked by radical species like H, OH, CO, and Cl. Thermal decay, just the molecule just falling apart, as well as a direct UV photolysis. So if you include all of those effects, you end up with this purple line over here. And the key thing to note is that the lifetime can actually be quite high. It can be up to 10 to 11 seconds in the middle part of the atmosphere. And that's because in the middle part of the atmosphere, it's relatively cool, so you don't have a lot of thermal decay. But you also it's also UV shielded, so you have relatively low UV. So if somehow you could hold a molecule fixed there for extended periods of time, it could live essentially forever. And it would be very, in that case, pH3 would be stable. It wouldn't need to be replenished. However, that's not how planets work, because molecules in the planet's atmosphere just don't hold still. They circulate and they move up and down. And if they move up, if they go up into the upper part of the atmosphere with the lifetimes of seconds or less, they're going to be destroyed. If you include the effects of this process, which is shown in this dashed maroon line over here, the lifetimes end up being a lot shorter. So if you include the effects of that process as well, those processes as well, you end up with this black curve over here, and that suppresses the photochemical lifetime of phosphine down to quite low numbers, down to the order of 10 to the 9th seconds or so in the middle part of the atmosphere where the phosphine was detected. So pH3 is unstable, in this case due to atmospheric transport. You can construct an extreme lower bound on the required pH3 production fluxes just by focusing on atmospheric transport to high altitudes. And if you use really conservative assumptions for that, you end up with a production rate of 3 times 10 to the 6th molecules per square meter per second. That's a really small flux. That's that's almost 100,000 times smaller than the production flux of methane on Earth. However, it's still quite high. And again, I want to emphasize that that this is an extreme lower bound. If you run a full photochemical model, you need about 1,000 times more. But we don't focus on this number over here because it's uncertain, because there's a lot we don't understand about Venus and about phosphine, as I'll get to in a little bit. So despite the fact that we're actually predicting you need about 1,000 times more, in our analysis, we focus on this extreme lower bound, which we think is a more robust number. If you even take that relatively low flux, it turns out that phosphine is really hard to abiotically synthesize, even at those relatively low rates. And that's the point of this other paper, this kind of interpretation paper that we also released coterminously with the observations paper. And the key takeaway there is that with what we currently understand about Venus and what we currently understand about phosphine, which I'll emphasize, we have a vast ocean of ignorance here. With what we currently understand about these molecules, we are not able to explain the formation of phosphine via conventional mechanisms. We evaluated processes like volcanism, and we found that based on what we understand about the mantle redox state of Venus, you would need an unrealistically reduced mantle, which doesn't seem to be present, to explain by many orders of magnitude, to explain the presence of phosphine on Venus. We looked at exogenous delivery, that is supply reducing phosphorus from above, from meteorites and comets, and we found that even if you made favorable assumptions about this process, you couldn't generate enough phosphine to explain the signature we saw. You don't reach that 3 times 10 to the 6 number. We looked at gas phase thermodynamics. The key thing there is that Venus is a relatively oxidizing environment. There's a lot of oxygen in the atmosphere, not free oxygen, not O2 like we breathe, but oxygen bonded to other molecules like the oxygen in carbon dioxide, the oxygen in sulfur dioxide, and so on and so forth. And as a consequence, as you might expect, gas phase thermodynamics is not able to explain the presence of phosphine in the atmosphere of Venus. The last thing that we looked at was gas phase kinetics. And this is perhaps the most important, but also the most uncertain of them all. The reason it's very uncertain is that most of the reaction rates that we needed to do this kind of calculation just didn't exist. So here I'm showing a schematic of our reaction network, our forward reaction network for the production of phosphine. The solid lines refer to processes that are quite strong, which we understand pretty well. We have good experimental constraints on the rates and the rate constants. The dashed lines refer to processes which we don't have strongly constrained, for which we've had to largely estimate the reaction rates. For most of these dashed lines, experimental measurements just don't exist. And so what we've had to do is we've had to extrapolate based on the reaction rates of analogous molecules. For example, the nitrogen-bearing analogs of these phosphorus species, which is an approximation that's commonly made. And what I want to point out to you is that this oxidized to reduced transition is very poorly defined. We have essentially no constraints there in the transition between phosphoruses connected to oxygens and phosphorus species connected to hydrogens, and even fewer as you kind of go up that redox ladder. So if you do that, so with those caveats in mind, if you do those measurements and then you kind of try to do sensitivity tests and explore the parameter space there, you find that from what we know of gas phase kinetics, as best we can estimate it, it also falls short of being able to explain the pH concentration by many orders of magnitude. Let me pause here for a moment and discuss for a moment the difference between kinetics and thermodynamics, because I understand that might not be something we all think about on an everyday basis. So thermodynamics is something that I think we're all relatively familiar with, and that's just Gibbs free energy minimization. It's the idea that if you take a chemical system and you give it an infinite amount of time, eventually it will evolve to the lowest energy state. The system will seek to minimize its own free energy. So that's what's shown in this plot over here. This plot is showing the total free energy of a system versus essentially time. This is a metric of time. So you have some set of reactants at some high initial free energy, and they want to decay down to a lower free energy state. And they'll seek the lowest free energy state they can, the global minimum in the energy surface. And given enough time, they'll tunnel through this reaction barrier and they'll collapse down to here. However, and this is exactly what happens if you have enough time, or alternately, if you're in a high energy state. For example, if you have high temperatures and pressures in your energy space, your system is going to be all the way up here. This barrier is going to be negligible, and you'll always end up collapsing down to this thermodynamically favored state. However, this doesn't necessarily happen, and it particularly doesn't happen in planets which have on rocky planets, on terrestrial planets, and that's because rocky planets, relative to, for example, gas giants, have cold, thin atmospheres. The temperatures and pressures there are not up here; they're down here instead. They're at much lower temperatures and pressures, and you end up in a regime where the reaction barrier is not negligible. The reaction barrier is, in fact, what dominates what goes on. It's a lot easier to. So this blue curve over here demonstrates an alternative pathway, a kinetic pathway. The kinetic products are at a lower free energy than the reactants, so the reaction is favored, but it's not quite as low energy as the final thermodynamic product. So in thermodynamic chemical equilibrium, the reactants won't end up in this state. However, under terrestrial planet conditions, it's difficult to achieve thermochemical equilibrium because you're down here. The reaction barrier is quite significant, and the reaction barrier dominates which reaction is going to happen. Because this kinetic reaction has a lower reaction barrier, the molecules will seek to go from here to here instead. The kinetic products will dominate. You'll end up in this so-called kinetically trapped state. It's true that if you then allow enough time, these kinetic products will then decay down to the thermodynamically dropped state. But frequently, you have external sources of free energy, for example, UV light, which will then pump you back up to high energy states. And so this is a very theoretical picture I've outlined, but it turns out to be what happens in planetary atmospheres. For example, just looking at our own Earth, the existence of O3 in our planet's atmosphere is radically out of thermodynamic equilibrium. It's maintained because UV pumps it up into that state. It's a kinetically trapped state. Similarly, the coexistence of oxygen and methane, as I mentioned before, is out of thermodynamic equilibrium by many, many orders of magnitude. It's again a kinetically trapped state. You're stuck in this state because of barrier limitations. Further afield in the atmosphere of Mars, the coexistence of carbon monoxide with the other atmospheric constituents is also significantly out of equilibrium. And there are many similar orders of purely abiotic equilibria pumped up in this kind of cold, thin regime accessed on the surfaces of rocky planets. And for the purposes of thermodynamics, even Venus's atmosphere is relatively cold and thin relative to the requirements for thermochemical equilibrium. So when you see work that's done here, including our own work, we'll often focus on the thermodynamics. And the fundamental reason for that is that it's easy. To do a thermodynamic analysis, all you need to know is the Gibbs free energy of the reactants and the products, and then you can do a minimization of this type. That's hard, but fundamentally it's doable, in large part because we have the Gibbs free energy of formations for most of these reactants measured pretty well already, particularly under the near conditions corresponding to standard temperatures and pressures. For kinetics, by contrast, you need to know you need to look up the rate parameters for each reaction. So for Gibbs free energy, for thermodynamics, you just need to look up one parameter for each reactant. For kinetics, you need to look up the rate parameters for each reaction, and each reactant can have many reactions associated with it. And the reaction rates can be dependent on a number of parameters. In addition to temperature and pressure, they can be dependent on what the third body is, the environmental context, for example, the temperature, for example, the pH of the salinity, an aqueous solution in the atmosphere, the amount of UV radiation, and so on and so forth. So kinetics is a lot harder. You have to have many, many times the number of free parameters and the number of experiment parameters you have to measure. And a lot of times those parameters just aren't measured. So it's hard to do kinetic analyses. However, as I'll try to emphasize in the later part of this talk, when you study the surface atmosphere system of rocky planets, you're in the regime that is kinetics dominated. So it's necessary to think about. So that's the kind of point that I want to emphasize over here, is that this gas phase kinetics is kind of a real unexplored country. We've done the best we can with the limited data that we have on these chemical species over here, but really, in my opinion, this is where the lion's share of new work needs to be done, is measuring the reactions of these species, taking these dashed lines and making them solid, and incorporating them into better photochemical models. So this kind of gets to the next question, which is that, okay, the fundamental point of our recent paper was to argue that Venus pH 3 can't be explained by conventional processes. So how can you explain the presence of pH 3 on Venus? Well, one of them, the thermochemical idea, is perhaps there's an unknown source of reducing power on Venus. Perhaps there's some mechanism by which you can get a lot of reductant, something that a lot of electron donor present on the surface of the planet. For example, some unknown source of hydrogen or some unknown source of Fe2+. If you can get a large enough source of Venusian reductant present, then that can act as a source of reducing power to convert atmospheric phosphorus species into phosphine. So that might be one way you can explore Venusian via pH 3. And the way to do that is more study of Venus, and in particular more observations and more missions. For example, the Shukriyan-1 mission that's been proposed by CIERA. Another example, which is one of the things that I'd really like to focus on, is unknown phosphine-related kinetics. And that boils down to the fact that in that plot I showed you earlier, there's just a lot we don't know about about phosphine kinetics. And in order to really understand the presence of phosphine on Venus, we need to make those measurements and understand and do a detailed chemical model, because we are in this kinetically trapped regime, and thermodynamics may not necessarily be a good guide. And this calls for more laboratory measurements and more ab initio calculations. There is, if both of these explanations fail, there is kind of the hypothesis of last resort, which is biological production. Biological production is invoked as a potential hypothesis because of where the phosphine is detected in the atmosphere of Venus. Specifically, the phosphine was specifically detected in the atmosphere of Venus at altitudes coterminous with the cloud deck on Venus. And the cloud deck on Venus is interesting because it's if there's a place in the atmosphere of Venus that's habitable, That's it. The surface of Venus is completely uninhabitable. It is at a temperature of many hundreds of degrees Kelvin. I think on the order of 600 or 700 degrees Kelvin, and at very high pressures, 90 times what we have on the surface. Taken together, these are conditions that are sufficient to melt lead and to sterilize any kind of life as we know it extremely robustly. So we don't think that that environment is anywhere near habitable for life as we know it. The upper part of the atmosphere is similarly uninhabitable in the sense that you're exposed to really large amounts of UV radiation, and you have very little access to micronutrients, to water vapor, and so on and so forth. Any of the requirements for life as we know it. The middle part of the atmosphere is, comparatively speaking, the most habitable part of Venus, in the sense that you have liquid water in the cloud decks, so you have a source of liquid water as a solvent. You have plenty of energy input in the form of stellar radiation, and you have the presence of micronutrients lofted from the surface of the planet. So if there's going to be life on Venus, the cloud deck is where you expect to find it. And the fact that the cloud deck is where you expect to find it. And the fact of the matter is that on terrestrial planets, the only other terrestrial planet where we know phosphine to be present in the atmosphere is Earth. And in Earth's atmosphere, it's present strictly due to biogeological production, which raises the hypothesis that perhaps, which raises the idea or the hypothesis that perhaps the pH 3 in the Venusian atmosphere is due to biological production of phosphine. So biological production of phosphine is not ruled out as a production mechanism. However, what I want to emphasize is that neither is it ruled in. So a lot of newspaper reports took this and ran with evidence for life on Venus, and we're not saying that at all. As I mentioned, there's a bunch of other mechanisms that we need to evaluate more closely first, essentially exploring the scope of our ignorance as to what might not be producing the Venusian phosphine. So based on everything we know about Venus, that phosphine shouldn't be there, but maybe there's something we don't know about Venus or something we don't know about phosphine, which can completely abiotically explain that production mechanism. And in some sense, an abiotic production mechanism is more what you expect from biochemistry, in the sense that, yes, the clouds of Venus are relatively habitable, but it's very much relative. It's only relative to the rest of the planet, because they are still a very uninhabitable environment overall, in the sense that, yes, there's liquid water there, but the liquid water there is present at extremely low concentrations. It's about 10 times drier than the Atacama Desert, and I'm not aware of any kind of microbe that we are aware of right now that can survive there, although that might just be a limit of our ignorance as well. Perhaps a more fundamental constraint comes from the very high abundance of sulfuric acid. There's a great deal of H2SO4 present in these cloud decks, and it makes it a very acidic environment, orders of magnitude more acidic than even the most acidic environment in which we observe life here on Earth, the Dalal Lakes in Africa. And we are aware of no extremophile, no form of life as we know that could survive there. So if life exists in the atmosphere of Venus in these cloud decks, it is unlike any life we have here on Earth. It may not even use water as a solvent, given how challenging it is to utilize water there. So what I want to emphasize is that biological production is not ruled out. It remains an option we should explore and consider for the presence of phosphine, but it's also not ruled in. The cloud decks of Venus are a very harsh environment, and it's not the kind of natural mechanism you should jump to. So what are the next steps? What are the next things we should be doing in following up this discovery? The first and most important thing is to confirm whether or not phosphine is in fact actually present. So what we've presented here is a single line detection of phosphine in the Venusian atmosphere. There's several things that could be done differently. One is that perhaps we just messed up our data analysis. So the first thing that needs to be done is an independent reanalysis of the existing data to confirm whether or not that phosphine is really present. And I know this is already underway because our data are all public, and I know that there exist teams out there that are already kind of scrutinizing this and seeing what they can do with it. Another thing to do is to search for other spectral features of phosphine at other wavelengths, and search for phosphine using other detection techniques, including in situ detection techniques, to confirm or refute this detection of phosphine. So the first thing we need to do is understand whether or not phosphine is really present. Assuming phosphine continues to be found to be present, then what we have to focus on is decreasing our ignorance about Venus in general and the photochemical kinetics of phosphine in particular. And we need to do this via laboratory experiments to characterize the kinetic processes of phosphorus and phosphorus species in the gas phase. And we need to do it by improving our understanding of Venus overall. if both of these, what I want to emphasize is that both of these steps can be done right here, right now, with instruments and facilities that we have available on Earth. If both of these continue to turn up negatives, if we continue to find phosphine and not be able to explain its presence, then that motivates a case for measurements and perhaps even missions to Venus to kind of characterize the phosphine production mechanism and really elucidate what's going on. I want to share with you a little bit of breaking news that's happened just in the few weeks since our paper was published to the archive. Groups have focused very intensively on identifying mechanisms on identifying ways to kind of either confirm or refute the detection of phosphine in the atmosphere of Venus. And there have already been some exciting results. None of these have been gone through the peer review process yet. Both of these have just been published to the archive, so take them with a grain of salt, but they're nonetheless interesting. One clever idea comes from the group of Rakesh Moghal at Cal Poly. And they had the bright idea of looking at the Pioneer mass spec data for evidence of phosphine. So many decades ago, the Pioneer mission launched probes through the Venusian atmosphere that had a mass spec on board to measure the chemical constituents of the Venusian atmosphere. And so all they did is they looked at this decades-old archival data and tried to see if they could identify evidence for the presence of phosphine in the atmosphere of Venus. And they actually find something exactly consistent with what we reported in our paper, which is that according to their analysis, phosphine and its photochemical fragments are in fact present in the Venusian atmosphere at altitudes corresponding to the cloud deck. So that's interesting. If true, it'll probably be the most dramatic and most direct validation you can get of the presence of phosphine, because that's an in situ probe. And it's not only detecting phosphine there, it's detecting the other molecules that you expect to be present as well. So that's probably the single strongest constraint you could get. But that still needs to go through the peer review process, and we need to be very skeptical about it until that's complete. Another potential probe was just published a couple of days ago, which is from Encrenas et al. 2020. And they again looked at archival data and tried to see if they could detect another transition to phosphine here at about 950 wave numbers. So their data are shown here in black. This is the emission spectrum of Venus that they measured. And if phosphine were present, it would create features around this wave band and have significant amounts of, and if it was present at 20 parts per billion, you'd get a dip about corresponding to this red line. And you don't see that dip over here by eye. So they do not detect phosphine in the atmosphere of Venus. They specifically rule out phosphine at concentrations higher than 5 parts per billion at altitudes more than 60 kilometers. So this is still consistent with the analysis of Greaves et al., because all Greaves et al. Said was that you should have 20 parts per billion somewhere between at altitude somewhere between 53 to 61 kilometers. And in fact, in our photochemical modeling, we find low concentrations of phosphine at high altitudes, but it's still worth taking a look at very closely. This is the kind of constraint we'd like to have, particularly deeper in the atmosphere, that can directly refute or directly verify the Greaves et al. Claim of phosphine based on the millimeter features. So just to, so those are the next steps. And to summarize the conclusions from this part of the talk, we have detected phosphine, we have reported the detection of phosphine in the cloud decks of Venus at a concentration of about 20 parts per million. This is unexpected because it's photochemically unstable and because you don't expect to find such a reducing species in an otherwise oxidizing atmosphere. We're unable to explain this detection with current understanding of Venus and of phosphine's photodynamics. So the next steps to kind of understand what's going on here is to first confirm whether or not that phosphine is really present, and a number of exciting studies are already underway on that score. The second is to explore the kinetics, to kind of narrow our uncertainties and our lack of understanding regarding phosphine and Venus in general. So in particular, we need to improve our understanding of the kinetics of derivative species of phosphine, like pH2 and pH3. And we need to scrutinize Venus for sources of potential reducing power. If all else fails, if phosphine continues to be present and we continue to be unable to explain its presence, then we have to fall back to it's worth evaluating the biological hypothesis further, perhaps with direct probes or in situ measurements. That's about all I've got. I'd like to acknowledge my funding sources and my colleagues and collaborators, and I'd love to take questions. Thank you.
Thank you for your nice presentation. I think students have learned a lot of things by your presentation. So we have got a few questions in inbox. So if you allow, we can start. So why actually why phosphine is important in finding life in other planets?
Okay, that ties back to kind of this slide over here. So the reason we're interested in finding phosphine on other planets, its positives as a biosignature is that it has no known geological false positives. In other words, for the processes that we are aware of for rocky planets that are similar to Earth, you don't expect phosphine to be produced by any mechanism other than life. So that is the fundamental reason people are interested in searching for phosphine on rocky planets. It's photochemically unstable, so it should be hard to find. But if it is present, then it's relatively hard to explain by mechanisms other than life as we know it. With their current state of ignorance, perhaps now we'll discover some mechanism for efficient abiotic synthesis of phosphine now that people are looking at it in more depth.
Thank you for your answer. We have another question. So, is there any possibility to find life
yes,
in
see
other
their entire
planets?
rest of this talk.
Okay. So, and this is the final question. What is the
Can you say that one more time?
volcanism? What is the
What is
volcanism?
Volcanism basically refers to the observation that there exist volcanoes on a planet, like for example our own Earth. These volcanoes are places where the material of the interior of the planet, like the mantle, reaches up through the surface. For example, due to mantle plumes, or because it's at a zone where the crust of the planet is relatively thin, and that mantle material can then be exposed to the upper part of the atmosphere. The upper part of the planet can be exposed to the atmosphere. When it's exposed to the atmosphere, that volcanism emits molten rock. As that molten rock solidifies, the gases that are contained within that rock are then exhaled. In other words, that magma as it cools emits these gases, and those gases go into the atmosphere. One of the hypotheses we evaluated is that volcanic activity could perhaps produce phosphine in this way, and the production rate of phosphine could perhaps be high enough to explain the observed abundance in the atmosphere of Venus. We found that for for volcanism rates that seem to be compatible with the existing observation and the existing constraints on the surface of Venus, the Venusian mantle is not reduced enough. It doesn't have enough hydrogen has too much oxygen and too little hydrogen to explain this signal.
So thanks. So I'd like to say thanks again on the behalf of the Department of Physics, Pabna University of Science and Technology. So I think students have learned a lot of things about this phosphine and the research on finding the life of other planets. So thanks again for accepting our invitation. So hope we will arrange another webinar with you in near future. So you are doing well in your research. So it's our pleasure actually that we can host you in our International Physics webinar. So thanks again.
Thanks very much. It's a pleasure to be here again, and thanks for the invitation to speak.